Let us solve one problem related to the design of pre-stressed concrete beam. The question is from November 2019. Let us read this question. Design pre-stressed concrete beam with following data. Span of beam is 10 meter. Live load is 25 kN per meter. Safe stress in concrete at transfer is equal to 17 Newton per mm square. Safe stress in concrete at final is equal to 14 Newton per mm square. Total loss of pre-stress is equal to 18%. Allowable tensile stress in concrete is 1 Newton per mm square. Safe stress in steel is equal to 1050 Newton per mm square. And you have to design the beam. Let us list out the given data. Okay. So the given permissible stresses are, okay, so safe stress of compressive nature in transfer loading condition is 17 Newton per mm square, 17 megapascal. Safe stress in compression under working load condition is 14 megapascal. Okay, so safe stress of tensile nature in transfer loading condition, safe stress in tensile nature in working load condition is same, it is 1 Newton per mm square. Okay, so as compared with the previous problem, in this question the bending moment due to dead load and bending moment due to live load is directly not given. In this question the totally dead load is absent, only live load is given. It is in form of a UDL 25 kN per meter, but span is given. So in this question you have to find out the bending moment due to live load and bending moment due to dead load. Okay, so loss is given, loss is 18%. So loss is 18% means loss ratio mu is equal to 0.82. Mu is equal to 0.82. Okay, so live load is given, it is live load is equal to 25 kilonewton per meter. Okay, let us calculate the bending moment due to live load. It is directly not given, so you have to find out the bending moment due to live load. It is live load into span square divided by 8 by considering the beam is simply supported. So this is the maximum bending moment at center. It is 25. Span of the beam is 10 meter divided by 8. So we get the bending moment due to live load is 312.5 kilonewton meter. Okay, so these calculations are you have to put in step number 1. Okay, this is a bending moment due to live load. Okay, then you have to find out the bending moment due to dead load. Okay, so B and D is totally absent, so B and D required to find out in this question. So first you have to put the sulfate of beam. Sulfate of beam is the dead load. Okay, so put it as width of the beam, depth of the beam and density of a pre-stressed concrete. Assume that it is 24 kilonewton per meter cube. Okay, so bending moment due to dead load is dead load L square by 8, assuming that the beam is simply supported. So dead load is width of beam, depth of beam, 24 is the density. Okay, so 10 square is the span square divided by 8. Okay, but assuming that B and D in form of mm, so we have to convert that value into meter by dividing 10 to 6. Okay, after multiplication you get the value, it is 300 B into D divided by 10 raised to 6, it is in kilonewton meter. Okay, so bending moment due to dead load is 300 into B into D, it is in Newton mm. So this is the calculation of bending moment due to dead load and bending moment due to live load. Now next step 2, step number 2, we know that the minimum sectional modulus. Okay, minimum sectional modulus Z, considering the section is rectangular section, so we know that Z is equal to Z bottom and Z top is same. So what is the formula for Z bottom? Okay, so formula for Z bottom is equal to bending moment due to live load plus 1 minus mu bending moment due to dead load divided by FBR. So we know that the FBR is the bottom fiber. FBR is the bottom fiber stress range. It is the range of bottom fiber stress. Okay, so FBR is calculated as, we know the formula. Okay, FBR is mu into FCT minus FTW. Okay, we know the value of mu is 0.82, FCT is 17, and we know that the FTW is the safe stress in working load condition but having the tensile nature, so you have to put here minus. So after simplification we get the value of FBR is 14.94 Newton per mm square. Once you get the FBR, so we know that Z for rectangular section, Z bottom and Z top is same, and that value is 1/6 BD square. Okay, so while putting the in this formula, the value is 1/6 BD square is the Z. Okay, we know the bending moment due to live load is 312.5 into 10 raised to 6. Okay, plus 1 minus mu is 0.82. Bending moment due to dead load is 300 BD. Okay, it is in form of BD because B and D is unknown, and we know the formula for value of FBR is 14.94. Okay, so in this condition you have to assume the width of beam is 250 mm. Okay, so you have to put the 250 mm this formula. Okay, it is 250. You have to find out now only depth. Okay, it is 312.5 into 10 raised to 6 plus 1 minus 0.82. Okay, so you have to put here put here 300. 300, width is 250 and multiplied by depth, divided by 14.94. After simplification, we get one quadratic equation. It is d square minus 21.69d, minus 502.08 into 10 raised to 3 is equal to 0. After the simplification, if we put this value here and simplify all these things, so we get the quadratic equation d square minus 21.69d minus 502.08 into 10 raised to 3 is equal to 0. The solution of this quadratic equation is 720 mm. So we get the depth of beam is 720 mm. Next, now clearly we get the width of section is 250 mm. Depth of section is 720 mm. So get the dimension of beam, width is 250 mm, 720 mm. Now we have to find out the actual values of dead load. So the actual value of dead load means it is the self-weight of beam. This is the actual value. So width into depth into density of pre-stressed concrete is 24. So it is 0.250 is calculated width, 0.720 is the calculated depth of the beam in meter, multiplied by 24. So what do we get the value of a dead load? The dead load is 4.32 kilonewton per meter. Considering this dead load, what is the bending moment due to dead load? What is the actual bending moment due to dead load? It is MDL, dead load, L square by 8, assuming that the beam is simply supported. It is 4.32 into 10 square by 8. So what is the actual value of bending moment due to dead load? It is 54 kilonewton meter. Also, to find out the actual value of a sectional modulus, actual value of sectional modulus Z. So we know that Z is equal to 1/6 BD square. So while putting these values, width is 250, depth is 720 square. So we get the actual sectional modulus is 21.6 into 10 raised to 6 mm cube. Now by considering all these actual values, you have to find out the actual stresses developed at top fiber and bottom fiber. Now exactly what is the actual stresses are. This is to include this step 3. Okay, actual stresses are, okay, how it is calculated. So f top, it is a top fiber stress. Formula is FTT minus bending moment due to dead load divided by Z top. So from this relation we get the FTT is minus 1. It is a tensile stress in transfer load condition. Bending moment due to dead load is 54 into 10 to the 6 and the value of Z top is 21.6 into 10 to 6. After simplification we get the value of F top is 3.5 megapascal, but it is minus. Okay, notice the actual value of F bottom. What is the actual value of F bottom? The formula is FTW divided by mu plus bending moment due to live load, bending moment due to dead load divided by mu into Z bottom. Okay, so the FTW is minus 1, mu is 0.82 plus bending moment due to live load is 312.5 into 10 raised to 6 plus actual value of bending moment due to dead load is 54.0 into 10 raised to 6, okay, divided by, it is 0.82 is the loss ratio and Z bottom is 21.6 into 10 raised to 6. After simplification we get this value, it is 19.48 megapascal. Okay, so this is the actual value of bottom fiber stress. Now you can fastly calculate the pre-stressing force. This is step number 4. So what is the actual value of pre-stressing force P? The pre-stressing force P is calculated. The formula is cross section area of a concrete F bottom Z bottom plus F top Z top, okay, divided by Z top plus Z bottom. Okay, so 250 into 720. So this is the actual dimensions of concrete. Z bottom and Z top is same. Z top and Z bottom is same. So you have to put common here, 21.6 into 10 raised to 6. Only you have to take the difference of F bottom 19.48 minus 3.5. Okay, and it is twice of 21.6 into 10 raised to 6 because this is the simple addition of this Z. So finally we get the pre-stressing force 1438.2 kilonewton. Okay, so then find out the area of wire required. It is pre-stressing force divided by safe stress in steel. Okay, so this is the safe stress in steel So pre-stressing force is 1438.2 into 10 raised to 3. The safe stress in steel is 1050. Okay, so from that we get the area of wire is 1369.7 mm square. Okay, if we assume the 6 mm wires strands. So you have to apply 49 strands or 49 wires in one tendon. If we assume the 8 mm diameter of wire, you have to put the total 28 wires in one tendon. Finally, step number 5, eccentricity of a tendon. Okay. Eccentricity of tendon, the formula is, okay, so Z top, Z bottom, F bottom minus F top divided by cross sectional area for concrete, F top, Z top plus F bottom, Z bottom. Okay, after application of all these values, okay, 21.6 into 10 raised to 6 square, because this is the multiplication. F bottom is 19.48 minus plus, it is 3.5. okay, so 250 into 720, these are the dimensions of a beam. 21.6 into 10 raised to 6, if you put common here, so FT minus FB, so 3.5, okay, 3.5 plus 19.48. so this is the total formula for E. Finally we get the eccentricity E, it is 172.64 mm. okay, this is the completion of this problem.